Thanks. So my name's Mike Collier, and I'm going to talk today about the shape of particle flux spectra on the surface of the moon, on the lunar surface, from photoions that have been accelerated to the lunar surface by non-monotonic potentials above the lunar surface. The spectral shape resembles a stairstep with a constant differential flux at low energies up to some cutoff energy determined by the lunar surface potential. And these types of spectral forms have been observed in the SIDE data, the superthermal ion detector experiment data on the lunar surface. SIDE are ion spectrometers set up on the lunar surface by the Apollo astronauts. Okay, this is what I was afraid of. Try again. Okay. All right, I wasn't told there was an on-off switch. Okay, I'll try it again. It's vibrating. I've got a phone call. All right, let's try again. Brilliant. All right, thank you. Okay, even prior to the Apollo era, investigators realized that, like spacecraft, the surface of the moon would become charged as a result of the moon's interaction with the space environment. And like spacecraft, the lunar surface charges positive on the day side because photoelectrons dominate, and negative on the night side because of the ambient plasma electrons. But just because the lunar day-side surface charges positive does not necessarily mean that the day-side lunar surface has a positive potential. All it means is that the electric field above the day-side lunar surface is positive. The day-side lunar surface can have either a positive or a negative potential. So in fact, there are two general forms that the potential profile can take above the lunar surface. There's the monotonic profile shown in red at the top, and there's the non-monotonic potential profile shown in blue at the bottom. And we're probably most familiar with the monotonic potential profile. In the monotonic potential profile, the lunar surface potential is positive, and it decays exponentially as you move away from the surface in a Debye-like shielding manner. The non-monotonic potential, shown in blue at the bottom here, for that potential, the lunar surface has a negative potential. It reaches an extremum at some distance above the lunar surface, and then decays asymptotically to zero at larger distances from the lunar surface. So Poppy et al. Have performed realistic particle and cell simulations of non-monotonic potentials above the lunar surface. And our goal here is to come up with an analytic model based on Andrew's results. And the premise of our analytic model is going to be that the potential profile above the lunar surface is determined solely by the photoelectron density above the lunar surface, which drops off with a scale length L. Okay, so under this assumption, we can integrate Poisson's equation twice and end up with the functional form shown here at the bottom of the slide. In this functional form, phi of x is the potential at a height x above the lunar surface. Delta V is the depth of the potential well. That is the difference between the lunar surface potential and the minimum potential. As I mentioned earlier, L is the photoelectron density scale length. E minus is the electric field far from the lunar surface. And finally, phi sub surf is the lunar surface potential. So we've compared this potential profile, this functional form, to the Poppy et al. Simulation results, and the agreement is reasonably good. In this figure, the solid line is the functional form shown on the previous slide, and the dashed line are the simulation results from Poppy et al. In this case, we're using a simulation from Andrew that has a plasma sheet electron temperature of 100 eV. Note that far from the surface, the potential profile is approximately linear, or the electric field is approximately constant. So we ask the question then, what would SIDE, the superthermal ion detector experiment, again SIDE is an ion spectrometer set up on the lunar surface by the Apollo astronauts. So we ask, what would SIDE see on the lunar surface due to photoions accelerated by non-monotonic potentials above the lunar surface? Now, photoions are accelerated to an energy that depends on where above the lunar surface they originate. So photoions originating close to the potential well have relatively little energy when they reach the lunar surface. On the other hand, photoions that are ionized far from the potential well are accelerated to almost the lunar surface potential. So the flux at the surface of photoions with energies between E and E plus delta E is proportional to the exospheric volume between the two heights corresponding to the energies E and E plus delta E. This is because the exosphere is the source of the photoions. Because the electric field is linear, that is the electric field is constant, the potential is linear, the flux between energies E and E plus delta E is proportional to delta E, or equivalently, the differential flux, which is the flux divided by the passband delta E, is constant. So the shape of the flux spectra at the lunar surface, due to photoions accelerated to the lunar surface by non-monotonic potentials above the lunar surface, resembles a stairstep with a constant differential flux at low energies up to a cutoff energy determined by the lunar surface potential. So again, this stairstep type flux profile is the predicted spectral form for photoions accelerated by non-monotonic potentials above the lunar surface. And in fact, we do see these types of potential profiles in the SIDE data on the lunar surface. And I've shown two spectra, two SIDE spectra here, illustrating this type of stair-step flux spectral form. Note that in both of these cases, the differential flux at low energies is approximately constant, And then at some cutoff energy, determined by the lunar surface potential, the flux drops off precipitously by over an order of magnitude in both cases. So these are two examples of these stairstep type flux profiles observed in the side data, but there are a lot more than two examples of these types of spectral forms in the side data. And if you haven't already, I encourage you to stop by Anna Newhart's poster. It's actually poster 36 in poster session 4, Dust in the Exosphere, Apollo ALSEP side observations of stairstep flux profiles in the terrestrial magnetotail. Anna is also a DREAM 2 team member, and she's done a very observationally thorough analysis of these stairstep type flux profiles in the side data. So stop by and talk with Anna. Okay, I'm almost done. Okay, in conclusion then, there are 3 points I'd like you to take away from this presentation. The first point is that this stairstep spectral form on the lunar surface is evidence of photoions accelerated by non-monotonic potentials above the lunar surface. And it's another of many techniques that allow us to measure surface potential and study the moon's interaction with the space environment. Secondly, Apollo era data are still teaching us about the moon, even after all of these years. I personally like to think of the Apollo ALSEP data as being akin to Shakespeare, in the sense that they may be old, but what they can tell us, the lessons they can teach us, what we can learn from them, is just as relevant today as it was in their heyday. And the final point I'd like you to take away from this presentation is that measurements of particles and fields on the lunar surface are very, very valuable. And I hope that we'll get a chance sometime soon to repeat and improve on the side observations. That is, to put an ion spectrometer on the lunar surface to get data, because the side data set is an invaluable and an unprecedented data set that keeps giving. So thank you very much. If you have questions at this point, I'd be happy to take them.